Let's take a few minutes to discuss the hydrogen deficiency index, and we're going to abbreviate this HDI, and this is a useful tool for predicting the possible shapes that our molecule might take on. And this is only useful if we have the chemical formula. So if we're given the chemical formula, we can calculate the HDI and then get an idea as to whether we should have rings and or double bonds and or triple bonds present in our molecule. So let's look at these four molecules that I've drawn on the page and just come up with their chemical formula. Here for cyclohexane, cyclohexene, 1-hexene, and simply hexane. And these chemical formulas should be pretty straightforward for us at this point. C6H12 for cyclohexane, C6H10 for cyclohexene, C6H12 for hexene, and hexane, C6H14. And so you can see that some of these differ by 2 hydrogens. If we compare the cyclohexane to the cyclohexene, you'll see that we lost 2 hydrogens in order to put on that double bond. And that's essentially what this technique is going to allow us to calculate or take into account. Here we lose 2 hydrogens. That accounts for the double bond. Let's compare cyclohexane to hexane, and you'll see again we lost 2 hydrogens. We had 14 in hexane. We have 12 in cyclohexane. So loss of 2 hydrogens can either allow for a double bond, as we saw before, or now it allows for a ring to be formed. So a ring and a double bond are essentially the same when it comes to simply accounting for those structural features in the hydrogen count. And we can look at that again. In hexene versus hexane, we lost 2 hydrogens as we went from hexane to hexene. Those 2 hydrogens account for the double bond here. So let's look at some other molecules that have more interesting features. Here we have butane, C4h10. Again, not very interesting, but let's add a nitrogen and see what we get. C4. Now we need to count carbons. It's a little bit more complicated. There are 3 here, 2 here for a total of 5, 2 more for a total of 7, 2 more for a total of 9, 2 more for a grand total of 11, and a nitrogen. And then with butanol, C4H10O, and for butyl chloride, C4H9Cl. So let's compare what's happened as we added other interesting atoms, heteroatoms, to butane. So we started with C4H10, and of course that fits our formula of C2H2N plus 2. So this is saturated. And how does the formula get affected as we add, say, a nitrogen? Well, if I just added a nitrogen to this 4-carbon chain, we see that the number of hydrogens had to increase by 1 to account for the fact that nitrogen has 2 more bonding partners as I add it to the 4-carbon chain. So a nitrogen will increase the allowed hydrogen count by 1. What happens if we add an oxygen to our 4-carbon chain? Well, that really, the way I think about oxygens is that they can just be inserted in between carbon-carbon or carbon-H bonds, for example. And you can see that's what we did here. We inserted this oxygen basically into this red bond. We have not changed the hydrogen count. We've simply added an O. So oxygens have no effect on our hydrogen count. And let's see, when we added the chloride, we essentially had to substitute for a hydrogen. So now we have 9 hydrogens and 1 chloride instead of 10 hydrogens. So the halogens simply act as a hydrogen. If we're going to count them up, we should treat them just like a hydrogen. They prevent our achieving the maximum number of hydrogens. So we can come up with a formula that you'll have to remember in order to calculate HDI. So we can say that the HDI is equal to 1/2 of twice the carbons plus 2 and minus the number of hydrogens. And you can see here, if we stopped there, we would end up with an HDI for butane of 0. Twice the hydrogens is 8, plus 2 is 10, minus the number of H's, minus 10, gives us 0 times a half is 0. And of course the HDI is designed to indicate how many potential rings or double bonds are present. We know there are 0 present in butane, and so this formula allows us to calculate 0 for a formula of C4H10. We also need to take into account the number of halogens, and we're going to treat those as X groups, so fluorine, chlorine, bromine, or iodine can be subtracted just like the H's are subtracted. And then we need to add 1 for each nitrogen. So essentially what we're doing here, this count is counting or calculating the number of allowed hydrogens for a given carbon count. And then we divide that by 2. If we had a deficit, we're going to get some small whole number integers. So let's look at that for the second compound here. So 2 times 4 plus 2 minus the number of H's is 11, minus the number of X groups, which is 0, plus the number of nitrogens, which is 1. We add that up, divide by 2, we should get 0. So we have 8 plus 2 minus 11 plus 1. That does equal 0. So we have 0 double bonds present. If you remember the formula for cyclohexene, C6H10, let's use that formula now in our HDI calculation. So 1/2, 2 times the number of carbons, which is 6, plus 2, minus the number of H's, 10, minus the number of halogens, 0, plus the number of nitrogens, 0. We add that up, we get 12 plus 2 minus 10 equals 4 times a half equals 2. So that our HDI for cyclohexene is 2. And of course, I hope you agree with that. We have an alkene right here, and we have the ring. So we have 2 potential double bonds and or rings present in this molecule. Let's look at these 2 formulas as for more practice calculating the HDI. So we have 1/2 times 2 times the number of carbons, which is 8, plus 2, minus the number of hydrogens, 8, minus the number of halogens, 0, plus the number of nitrogens, 0. We add this up. We get 16 plus 2 minus 8, and that equals 18 minus 8 equals 10 over 2. So this molecule has 5 HDI, 5 hydrogen deficiency index. So it's going to be a pretty interesting molecule. We'll probably need maybe a ring and or a triple bond. Let's see if we can come up with something like this. So an aromatic ring, as you can see here, accounts for 4 on your HDI number. So if you have an HDI of 4 or more, it might be safe to think that there's an aromatic ring somewhere. And then I have 2 more carbons, and if I put, I counted for 4 here, so there's my 5th ring and or double bond. So this could be styrene, which is a vinyl benzene. It has an HDI of 5, and it has only 8 hydrogens. Let's look at this final formula here. We want 1/2 times 2 times the number of carbons, which is 10, plus 2, minus the number of hydrogens, which is 9, minus the number of chlorines, which is 2, plus the number of nitrogens, which is 1. And again, we ignore the oxygens because they don't change the hydrogen count, the allowed hydrogen count. So we're done with our formula. We can do some math. 20 plus 2 minus 9 minus 2 plus 1. 20 plus 2 is 22, minus 9 is 13, minus 2 is 11, plus 1 is 12, over 2 equals 6. So this formula here has an HDI of 6, meaning I need a combination of 6 rings, double bonds, and or triple bonds. So before we finish this video, let's just point out that a triple bond gives us an HDI of 2, because there's 2 double bonds, there's 2 pi bonds in that triple bond. So if you have a triple bond, that accounts for 2 of your HDI count. So just keep this HDI concept in mind as we discuss the NMR chapter. When we know the formula, using the HDI can give us a large number of clues as to the potential allowed structures that our molecule can have.